Log on, tune in, find out. Another good idea from Cambridge.
Speaker today is Professor Prakash Belkale from North Carolina. He's going to talk about geometric unitarity of the KC Hitchin connection on conformal blocks in genus 0.
Thank you for this, the invitation to visit Newton Institute and for this talk. Can you hear me? Yeah, good. Okay. So I'll start by setting the main players in this, and then describe what I'm going to do. So I'm going to fix a simple Lie algebra. So G, simple Lie algebra, characteristic 0, over C and all that. So you may want to think about SL2, for instance, if, or any of the others. So I'm also going to fix n highest weights for finite dimensional irreducible representations of G. So lambda 1 and n highest weights for finite dimensional irreducible representations. Okay, so finite dimensional of level less than or equal to k. So the level. Okay, so that means that lambda comma, so that means that the inner product with the highest root is less than or equal to k, where this thing has to be normalized. So theta comma theta is equal to 2. So I have this data. Right. So associated to this data, there is a vector bundle of conformal blocks or generalized theta functions. So associated to this, there exists a vector bundle of conformal blocks, or generalized theta functions or non-abelian theta functions and so on, on MGN, on the moduli space of G. So I'm going to be working only on the smooth part. So smooth genus G curved with n mark points. Okay, so smooth. N mark points, distinct and all that. Okay. So I'm going to call this V, okay. And this has a flat projective connection, so with which has a projective connection. So to link it up with other objects that or moduli objects, so let me give the standard interpretation for these things. So the fiber. So let me just for as an take n equal to 0, but really my talk will be about n is not equal to 0. But but sort of to view these objects. And let me take C in MGN. Okay. So the fiber of this bundle over C has actually has two meanings. So one is as global sections of over the modular space of principal G bundles on the curve, and the power of the generating line bundle. So principal. What is that? This is so this is one interpretation, and the other interpretation is closer to my talk really. So it's in terms of representation theory. So also representation theory. So this is the one that I will follow in this talk. So this can be written as a double quotient. So you choose your curve, and you choose a point on it and a local coordinate here. The principal bundles on C, they become trivial on the complement of a point. So and you can think of forming all of this as a double quotient by the patching function. So it's so G is the associated group for the Lie algebra. So it's G. So there's ambiguity in the patching. You can change the patching on the complement and in a disk around it. So and this thing is usually called the affine Grassmannian. It plays the role of a G mod B in this theory. So this is like a B. And you can, I mean, all this needs to be made precise. I mean, but at least we can see the basic relations. So this is dominated by QG. Thinking really stack here, right? So and you add this line bundle, so one can formulate the following type of theorem. So VC is 0 QG pi upper star. So this is pi upper star L to the K. So I pull it up, and then I still have to take invariance with respect to this. Minus P. And this turns out to be an irreducible representation of not of this group, but a central extension of it, a dual of any radius of let me write Lie algebras now. So G hat a central extension of G tensor functions. So, I mean, of course, all this needs to be made precise, right? I mean, and this has been done. That's, okay. Right. So this basic object we are studying can be viewed in this way and in that way, and that's closer to what we're going to discuss today. So now, the aim for this talk is the following. So for G equal to 0. Okay, the genus of the curve, so it's this really projective line with n marked points. So for G equal to 0, there's a hypergeometric local system on really configuration of n point, but let me write a little bit vaguely as m0n. So I'll define all these things. So one of the first things I'll do is define that local system without, I mean, the hypergeometric local system right away. But let me write out and a flat injective map. V to L, which lands in such injective. So this hypergeometric local system will carry the Gauss-Manin connection. With image in let me I mean, I'll make this more precise, LM0. So like sort of holomorphic M forms. So this sort of situation is very unusual. You will not find anything in M0 parts of cohomology which is preserved by the monodromy. So it's a slightly unusual situation. So all this will be made precise. So before I do that, so let me write some names here, so in the order of appearance of their papers. So Sheckman, Vachenko. So these results use 90s. No, 90 perhaps. Gavetsky and Ramdas, so who proved the statement for SL2. And it's this approach that I'm following. So there are detailed discussions of the relations between what I'm doing and what Ramdas is doing. But the main difference is that instead of using geometry of chord schemes, I'm going to be using representation theory of G, of this Cosmodi group. Okay? So chord schemes replaced by, but other than that, the arguments are replaced by. Yeah. And Ramdas works on a physics proposal of Gavetsky. Okay, so we will get to that. Okay, so my first aim is to before I do that. Is to note a consequence of this, which is which is that it gives this this V a unitary structure. Yeah. So consequently, V are unitary structures, explicit unitary structure. So I'll again at the very end I'll write out formulas, because it's landing in M0 part. You can use the Hodge form on cohomology to get a unitary form, explicit unitary. Yeah, definite. Yeah, unitary metric. Let's say, yeah, on V. Okay, so now such unitary metrics are already available. So unitary structures. So we are available thanks to quantum groups. So obtained can also be from quantum groups. So this is something that I don't know much about really. And so this is the approach of Kirillov and Wenzel. This is in the 90s. And I came to know of it very recently. I mean, by Kirillov. So nothing has been written up yet. So I hope for a detailed exposition. Okay. So this works in all genera, but the metric obtained is not explicit. It's not linked to hypergeometric local systems. So not explicit. So all genera. Not explicit, not linked to hypergeometric. Local systems, or any Gauss-Manin local systems. Okay. But it's all genera. Okay, so now my first aim is to describe the local system. Okay, so the local system is not hard to define. So so I had this n weights, right? So in the beginning I had lambda 1 till lambda n. So unless the sum of them, these guys, is in the root lattice, there would be the conformal blocks would be empty. So I'm going to make this condition. So I equal to 1 to n is the sum of simple roots, perhaps with multiplicities, simple positive root. All right. So I'm going to choose a particular ordering. So A equal to 1 to m. So the number of points was n, and the sort of the new number of this is a new number. So there's n and m. Data. Okay. So I have this combinatorial data. So and also let me fix z1 till zn in A1. So somehow I already chosen infinity and coordinates on the rest of the points. So I have this. So now what we're going to do is we're going to add new points. Consider a to the m. So you're going to add these many new points, a to the m, and the coordinates are t1 till tn. And I'll write out a function that gives the hypergeometric local system. Right. So there's this it's called Shekman-Virchenko master function. So the function is the following. So it's a multi-valued function. So R is equal to less than G. Yeah. The first factor is actually not important for us, but let me, since I'm going to name it this way. So kappa is equal to the k, which was the level that we had, plus the dual Coxeter number. So this depends upon T1 T's and the Z's. So dual. So I mean, it's equal to 2 for SL2. Yeah. It's not a very number. Okay. So that's one factor. So this is the interaction between the Z's, and then there is an interaction between the Z's and the T's, the new variables that are added. I and A, Zi minus T. There's an exponent again, minus lambda I beta A. So this is the killing form. So whatever I'm writing here, this is the inner product in the katan, so the dual really.
The star is capital K or no? There is a star in the formula which is rather mysterious.
Oh, this exponent?
No. Lambda J over
Kappa. Ah, yeah, okay, right. Yeah, this doesn't deserve, there's no more. It's, I mean, it's different. I think it's, somehow I got committed to using K. The better thing would be to use L, I think, and have not have this trouble. Yeah, so it's important that it's not little k. Okay. Yeah, so it is Ti minus Ta minus Tb, A less than B. So minus beta A, beta B over kappa. Oh, well, again. Okay, so the way to think about it is that to each of these you have associated a simple root, so beta 1, beta m, and you've done that once and for all. Okay, so this simple root is associated with the first one, and you have this function, and right. So we can so we can let yz equals cover of am minus various diagonals, right? So am minus Ti equal to Zi, Zj, Ta equal to Zj, Ta equal to infinity, Ta equal to Tb, right? Remove all those given by R. Okay. So that means that you introduce a new variable whose kappa power is what's there. That's okay in SL, and there's these things could also be fractional in some systems, so then you'll have to multiply a bigger power of k. I think this should be clear. It may be disconnected the way I wrote it. So why is this? So you get a family of varieties over a to the n, and this is the hypergeometric local system. Okay, right. So in fact, but it's going to be a little bit better than this. So we can choose a compactification. So the local system that we'll be considering is that. So yz bar compactification of yz. Smooth compactification. So the way I wrote it, this is actually smooth because it's unramified over the. And you throw away all that. Okay, so and then so that the hypergeometric local system is so L equals Hm yz bar. In fact, it's not, it's going to be the map from V to L, which I'll describe next, will land in Hm0 yz bar to say. Okay, so which I haven't yet described. And this part would also inject in the thing without the bars. So I'll come get to that later. So hopefully the hypergeometric local system should be clear now. So the next step would be to describe the Okay, so the next step is right. So before I go on, things like this, they don't form local subsystems usually, because of the Griffith's transversality. Right. they could land in m minus 1 comma 1. But there's something so special happening here, and I'm not saying that this surjects onto this part. Okay. So map V12. So this is the important map V12. Okay. Right. So that's the usual kind of problem with trying to make Hitchin connection motivic. How to find a map from the Hitchin system to some motivic local system. So according to Gawetsky and Ramdas, one should proceed as follows. So it's a general strategy. So which should apply for in all genera and so on. But, okay, so. So the strategy is as follows. So the first observation is that so we start with this interpretation that VC is H0 mg C n to the k. Okay. Right, so you can think of it this way, and so let's take up an element here. Now this element vanishes on the non-semi-stable part here. So psi vanishes on the non-semi-stable points of MGC. It's kind of a basic property of invariant theory that these guys would, that's the. Sorry, let me not go. This is a. If you think about it, this the way these functions are kind of single out the semi-stable part, and the non-semi-stable ones vanish on this thing. So once you have this, so the next step is fix a so according to them, so fix a. I'm going more by Ramdas's interpretation. Okay. Fix Harder-Nursimon stratum in MGC. So these are places where the non-semi-stable, right? So Harder and Nursimon stratum in MGC. So and of course these guys would all vanish. So the point is somehow to take a suitable multi-derivative. So take a suitable multi-derivative. Principal parts, right? Of psi. Now, so next step is to interpret such an object as an algebraic differential form. So the principal part of course should not vanish, so you get something non-vanishing out of this. So and then this is the kind of, it's of course not precise, right? So each Harder-Nursimon stratum should therefore lead us to top degree differential forms. So should assign to psi a top degree differential form. So we'll see it in examples how this goes on a smooth variety. Okay. So then the hope is that such a thing would extend to compactification. So the form should extend to compactification. So in the example that I'm going to give, which is the theorem, this works out. And then not just that, you get form should then you need a kind of flatness as well. This is kind of a very difficult step. Hope they give flat. Yeah. Yeah. Okay, so I don't. So in various papers of Gawetsky, it's worked out for higher genus as well. Using, I think in one of them he uses work of Bertram and Thaddeus to get till here. I think maybe not here. Okay, so but I'm going to be working in genus 0. And so I'm also going to be using this the language of the work of Tsuchiya, Ueno, and Yamada to carry out this in the language of representation theory. So I think the first paper was Tsuchiya and Kani. Okay, so right. So what should I? So the way it comes out from that analysis that this form should be a correlation function. Yeah, so it turns out the form that we're going to get in this language. So now I need to get into a little bit of this. I think. So the point is to just kind of set up this strategy in an algebraic language. Okay. So let me now give a brief introduction to the conformal blocks following Tsuchiya, Ueno, and Yamada. Okay, so right. I mean, so the derivative. So the way one should think about derivative is you're going to be modifying the principal bundle at a few points, and then taking it and then flowing along that and taking a suitable partial derivative. Yeah. So okay, but this is the key statement that I want to explain. So let's work with some infinite dimensional Lie theory. So G hat says G tensor sub CC, the central extension of that plus CC, and C is central, and the Lie bracket is given by the following. So X tensor F XY G plus, of course, plus XY residue psi equal to 0. Oh, wait, let me use psi equal to 0. GTF. I mean, of course, this is the key term. Okay, so from this. So in some sense, the associated group of this is what acts on the line bundle L that we had earlier on MGC. I mean, so once you pull up to QG, this is the group of this acts on the line bundle. Okay. But you know, it's not necessary to know all that here. Okay. So now I want to introduce some notation and little bit about the representation theory of this. So it's the notation. So X in G is X tensor. That's the size of the parameter here. Okay, so now the next topic is the representations of this. So first let's form this set. So Pk is lambda dominant integral weight for G. For G with level less than or equal to K. So lambda. So and then so associated representation, I'm going to write it as V lambda. So associated representation. Now each of this also give us each of this data, they give us a representation of G hat as well. So the elements lambda and Pk give representations of integrable highest weight representations H lambda of G hat. So that I mean, when you have highest weight, you need to know what the Borel is. The Borel is G plus equal to G tensor S. Okay, so and those are going to be called H lambda, and H lambda contains V lambda, and I'm going to choose the highest weight vector and denote them by this highest weight vector. Okay. So bracket notation. Okay, so we have so this is the basic representation theory. Now we need to define conformal blocks, and we'll need to take endpoints on P1 and define objects. In fact, this works for any curve, but let me do it only for P1. Okay, so conformal. Right, so we're going to fix endpoints as before. So the endpoints on A1 distinct Z1 till Zn, and we also have representations lambda 1 to lambda n. So we're going to form a kind of multivariable version of this. So G hat n, and let me introduce local variables Z minus Ci. So G hat is direct sum. G tensor C. So it's almost like the one, but I don't have n k copies of C, just one copy, because I'm going to have all the levels be C. Maybe so the k comes out this way. So C acts by k on k on each lambda. Okay, multiplication by k. So right. So we have this object, and then something to remember the global geometry of the curve. So g of chi. So chi is this marked chi equal to v1 and along with the coordinate, which we'll ignore because we have natural coordinates. So g of chi is g tensor functions on p1 minus z1 till zn, which sits inside G at n by local expansions at each of these points. So and now we can form we have also these representations. So let's form this tensor product. Okay. Tensor product of these. So H lambda was this highest weight representation of G hat. Okay. So lambda was in pk. Right? All these guys are in pk. So this is it. And so G hat n acts on this. So you can. So we can now define conformal blocks. I'm following the notation of Tsuchiya, Ono, and Yamada. So this is the marked curve which remembers those endpoints, and these are the representations, and this is to say dual. So it's homomorphisms from H lambda. So H lambda was this tensor product, and so this is of course an infinite object, and we want to cut it down to finite dimensions. So it's a finite dimensional vector. So a finite dimensional vector space. So this object sort of remembers the endpoints on the curve. And in fact, in genus 0, this also sits inside the tensor product of the v lambda of the duals. You take the invariance with respect to G. So this is only in genus 0. So recall that v lambdas were the finite dimensional representations of G. So here we have these objects. Right. So there's a bit of notation. So things here are written as this way, and any object here I'm going to write it as something like this, and then the pairing is psi comma phi. Okay. So these are conformal blocks, and they sit inside here, and in fact the connection can be described on this. So connection. KZ connection, the first of these connections on this tensor product, and it restricts to give a connection on this on the tensor product. Okay, so this is so these are conformal blocks. Right. So maybe in the notation that I was writing before, so maybe this is sort of more formally analogous to this one. Okay. So I mean, of course they're kind of explicitly given, and it's possible to describe what they are inside here without going to infinite dimensional geometry. So you probably specify exactly which part of this is spanned by this. Okay, so one of the basic properties of this theory is propagation of vacuum, which will help us find these forms. So we are on our way to find, given an element psi here, we're on our way to produce a form from it on a variety on YZ. Right? So that's our aim. So the first step is propagation of vacuum. I need to recall that. So propagation. Vacuum. It just says you can add a new point. So add a new point P different from the Zi's, and the representation associated is 0. So the H0 is not 0, because I mean the finite dimensional representation is trivial, is C, but H0 is not C. Okay, yeah. So we add a new point, and then the statement says that the things have not changed. So, so this is the new point and the extra representation there and chi prime. So this is P1 Z1 Zn T, and the associated representations are lambda 1 to lambda n and 0. And in the language of this Bra and Ket vectors, so if you have a psi here that goes to psi hat, then the rule is very simple. Psi hat, it acts on a tensor product which maybe this way. So it should act on a bigger tensor. So it's you act on a tensor in H lambda. Tensor the vacuum vector equal to psi comma phi. Okay. This is the compatibility. Of course, one needs to show that this is meaningful. So this psi hat is supposed to act on one more tensor summand, and the rule when it's the vacuum vector. So this is the highest weight in H0. Okay, so now the point is that we can now add any number of points and then get differential forms from this. So recall, so we had using the earlier notation, so lambda is equal to sum of beta a equal to 1 to m, I equal to 1 to n. So we're going to add m new points. So propagate vacuum to m new points. To T1, T2, Tn, m new points, one for each one of them. So and then now we are allowed to, so we get from psi gives you a psi hat, which so it can now act on things which have a tensor which is m plus n. So it acts on an m plus n tensor, any m plus n tensor, a suitable form. Okay, so and the choice for these tensors are kind of, it's clear. So let me define it. So we added new points, and Right. So we're going to define. So define omega of psi, which is again a differential form on a to the m, the space of T1 till Tm. So it's going to be this psi. Now, so on the last n points, I'm going to just take the highest weight vectors of the corresponding representations. But then I'm allowed to do things at these points. So at T1, instead of taking the 0 vacuum vector, I'm going to take this one, so f beta minus 1, 0. Okay. So this is I'm going to assume a Cartan decomposition of G. So the f betas, e betas, and this stands for f beta tensor psi minus 1. Okay, so tensor f beta n. Okay. So and it's sort of the in work of Suchi, Ueno, and Yamada, the notation is the following one. So of course I need to plug in dt. I mean, this one does not have it. It's assume that it's a form. Okay. So what does this correspond? So in this language of converting things on the moduli space to the in terms of conformal blocks, this is saying that you're modifying the trivial principal bundle at these additional points. So it's equal to a suitable derivative of psi along the simplest Harder-Nasuman stratum. So where the principal bundle is actually trivial and the parabolic structures are trivial. Okay, so it needs to. So just to recap, so there's this propagation of vacuum which allows you to add one more point and then add m more points and then differentiate in these m points in these directions there. So these are things that kind of take you out of being unstable. These are directions which will just kind of trying to get you out of the Harder-Nasuman stratum and modify the principal bundle at these points and then take a derivative. And that's the idea. Okay, sorry. I get that. So now I can state that. So this is the form, but of course it still needs to be multiplied by the Sheckman-Wachenko form, master function. Okay, so define. So tell me I should so for psi in this is the original conformal blocks. So the form R omega psi. So maybe I'll start writing omega, just omega for this, not like this. So I got a form on a to the m, right? So this is a form on a to the m, and this is the Sheckman-Wachenko master function that I wrote earlier. So the form extends to compactifications. So this actually lives on yz, so it's actually a form on yz extends to compactifications. Okay. The first part. Right. So now let me draw a picture with various objects. Okay, so the second part is the following. So we have the following kind of picture. So V lambda chi so sits inside. So this is the compactification yz bar. So remember that, recall that yz was the the covering of a to the m, minus all those diagonals, given by this multivalued function. So I'm going to write that statement in the following way: omega m y sigma. And this sits inside hm of yz. This is, I mean, all these statements are the scheme of this is taken from Ramdas's paper. So this is due to this part is due to Lilin, and this is what one says. And this map is actually, so this is what Sheckman and Virchenko proved to be flat with respect to connections. So this is flat for connections. And a little bit of work shows that the map that one has to the compactification is again flat for the so 3 hm is flat for connections. The third. So now I want to write the metric. Of course, you have the Hodge form on this one, which is definite on the m0 part. So that's all we're going to do. So the metric, unitary metric. So unitary metric is so probably a power of I. Right then. Well, you can put either a to the m or yz. I mean, because what I'm going to write is a single valued. Unitary. Yeah. So this is so converges. It's a consequence of the extension to compactification, and this was conjectured by Gawitsky and co-authors. Okay, so the way the metric comes about is really the Hodge form on yz bar. Okay, so the key step is, of course, is to prove a statement like this, that the form extends to compactification, and I want to say a little bit about that. Okay, so ideas in the pool. So of course R has zeros and poles, so maybe I should recall what R looked like. Ignoring the z factors, zi minus ta lambda I beta a over kappa. I mean, I'm ignoring the interaction between the z's, which is not important here. Ta minus tz I less than b. Of course, this has zeros and poles, fractional zeros and fractional poles. And one thing one knows is that omega is a log form. You can actually write out an expansion for omega. In fact, the form given by Sheckman and Virchenko for this is obviously a log form. Okay, so but still one needs to have omega vanish on various. So the method is the following. So you need to show that on various strata the logarithmic degree of R omega is positive. So on the strata T1 equals TL, or T1, various points come together equal to Z1. No, maybe I mean just or any of the Z's, or T1 equals TL equals infinity. the logarithmic degree of r omega is positive. This is what one needs to show that it extends to compactification. These are the essential strata. Okay, so so you need to somehow control this, and so using this the work of Tsuchiya, Owen, and Yamada, one can write power series expansion. So one can write power. So one of the ideas in the proof is to use power series expansions. So let me give you an example of that. Okay, so T1 TL approach Z1. Okay, so now let me introduce these variables ui equal to Z1 Ti minus Z1. Okay. So one needs to make sure that this has enough zeros to compensate for the pole behavior of R. For instance. Right. So then there's a power series expansion of the following type. So omega is equal to also on an angular sector. Okay. Angular sectors. So unless I got it wrong, I mean the one that I'm using is UL is the smallest one. UL minus 1. Okay, so you have minus B1 minus 1 omega B, because and the point is that there's a formula for omega B. So these are all B's, because we don't really want too much pole. So one needs to sort of make sure that the sum of the B's doesn't get too big. So the first there's an expression for the polar term, in which so the points after L, they don't really matter. So they let me beta m Tm. Correlation function, but now I'm supposed to put n new vectors here, n vectors here. The first vector is the one that's important because they're all approaching Z1. It's equal to f beta 1 B1 f beta L BL applied to lambda 1, and then the rest of them are similar. So it's this term. So this is the term that's causing this polar term. Now the second part is criteria for vanishing of these things. Right. So this lives in V lambda 1. No, rather H lambda 1, and this is in V lambda 2, and so on. So still you are in infinite dimensional representation theory, and this vector properly is here, but we have criteria for when it vanishes. So again from representation theory of Kac-Moody groups, vanishing criteria. So the following. So maybe suppose this is not 0, then lambda 1 not equal to 0 implies you don't want the pole term to be too large. So I hope I get the inequality right. So summation BA, right, this is how bad the pole is getting. Is less than or equal to a certain quantity which can be controlled kind of effectively. So it's 2 times lambda 1 comma gamma minus gamma comma gamma over k, not kappa, where gamma is the sum of betas. A equal to 1 to L. Okay. So this is sort of this bound is very similar to the exponents that are appearing in similar to exponents in R. But there's a difference. It's k here and not kappa. In fact, it's kind of optimal that it appears here. So using these things, you can make sure that a huge pole cannot really occur because those terms are really out of the picture. Okay. So this is one of the method, and this uses kind of integrability of this representation. I mean, fact for integrable. So it's analog of the fact for representations of finite dimensional Lie algebras that the highest weight is the highest weight, that its norm is the largest among all the norms that appear in the representation. So this is strictly analogous to that in infinite dimensional representation theory. Okay. Right. Okay. So maybe I mean, so there is so let's see. So in the case of SU2. Right, so SL2 rather. Well, there are no so what happens is this is much simpler if you work it this way. So so there are no poles as T1 approaches T2 and so on. Okay, so in general, there's a pole in this omega, poles in omega. There's a pole as Ta approaches Tb if and only if beta of A plus beta of B is a root. Okay, so omega, so T pole at Ta equal to Tb implies beta of A plus beta of B is a root. And the situation is very similar, and sort of the main point here is that in the Cosmode groups this relation holds. Implies omega vanishes on codimension k diagonals. This is what Ramdas uses. But he uses the geometry of code schemes to get to this statement. If you view it in representation theory, it's a consequence of relations like this. But in this case, there are some more complications because the roots can get together in various different ways. And so before I finish, I want to sort of say some questions. So one of them is his higher higher genus. So one of the difficulties is the absence of analog of Shechtman-Wadchenko theorem. So no known analog. And another reason is that the proof of Shechtman and Wadchenko doesn't sort of use the universal properties of Hitchin's connection. I mean, so maybe one of the things to obtain is a proof of Shechtman-Wadchenko using universal properties of Hitchin connection. So I mean, this is, I think, even in genus 0, this would be nice to. So this is not. This is kind of one of the difficulties. Yeah. So maybe one last question is: so there are metrics now in genus 0. So do strange dualities preserve the metric? Okay, maybe we should stop.
Questions or comments? Well, no, thank the speaker again.